Okay, we teach electricity and magnetism in kind of a classical way, and we're doing it by starting with observations. So when we're dealing with observations, we know and we've observed that for electricity, we can have something that's a positive charge, and we can have something that's a negative charge. And we're all going to get mad at Ben Franklin because Ben Franklin picked wrong. When we talk about a charge carrier, Ben Franklin thought the charge carrier was the positive charge. He got it wrong. He had a 50-50 shot and he blew it. We now know that our charge carrier is the negative charge, and the negative charges are an electron. And it's the electrons that are free to move. Our positive charges are our protons. And our protons are stuck in the nucleus and they can't move. So from a materials point of view, it's the electrons that are going to be our charge carriers that actually move. And we're going to be dealing with this. But as we start talking about things like current and we start talking about other things, we just figure out that Ben Franklin guessed wrong and everything's going to be kind of backwards. So one of the things that we do know is we have a positive charge and a negative charge in some observations. One observation is if I have two positive charges, they're going to repel. If I have two negative charges, they're going to repel. But if I have a positive and a negative charge, they attract. So we already have an observation that things are going to work. So we start with our positive charge, and if I were to draw my field, I'm going to draw my field lines. I'm going to draw my arrows representing my field, and they're going to go away from the positive charge. And we can actually get that field. Similarly, if we were dealing with gravity, so this is the Earth, we have a field force that's gravity, and it comes in this direction. So these are going to be representing our fields, and we can actually draw our fields, and you're going to get some practice dealing with that. But we're going to have our positive charge. We can talk about things like conduction. Or conductors. And if I look at my periodic table, these are my nonmetals, and these are my metals. We know that metals are good conductors. Metals are good conductors, and our best conductors for wire are going to be in here in the transition elements. And the reason that this is where my best are is because these are d orbitals, and these have metallic bonding. And if we think about these have a lot of electrons that are in their outer shells. And because of those energy levels in the electrons, one atom right next to the other atom may or may not know who has the electron. And this becomes kind of what I call electron soup. And that's going to allow those electrons to move. And when we move those electrons, we're going to start to see static electricity, we'll see conduction, we'll see current, we'll get a bunch of those things, and we'll talk more about that as we go on. But this is really what's happening. So we have the other part of this is we have conductors, we also have insulators. So, and well, basically what we say is if I can conduct my electrons, we have conductors, everything else are insulators, and that allows us to work through things. The other thing is that electric charge is conserved. And if you think about it, we got to know where our electrons are going. If I'm going to start out with 10 electrons, I'm going to finish with 10 electrons. So my electric charge is going to be conserved. The other thing that we know about electric charge is they're quantized. And we know they're quantized from the experiment that was done. And this was the Millikan oil drop experiment. Let's see if I can spell today. And what happened was he would take 2 charged plates and he would get an oil drop and he could measure the volume of the oil. So he knew what the weight was and he could get these to suspend between the fields and he could calculate the number of electrons on the oil drop that was there to keep the balance. And by calculating that number, he could actually infer what the charge on an electron is. So we can do that. So we can charge things up a couple of ways. We can charge by conduction. And think of that as actually physically touching. And we can charge by induction. So this one makes more sense because this explains why your balloon is going to attach to the wall. So I've got my balloon, I've rubbed it on my head, and for grins and giggles, we're going to say it's positively charged. As I bring that balloon to the wall, my wall is neutral. So I got positive and negative charges here. I got positive and negative charges. I got positive and negative charges. I got positive and negative charges. But as I bring my balloon in, my positive charges are going to want to run away because they repel. But my negative charges are going to stay at the top. And so there's going to be an attraction. And this is what charging by induction is talking about. So charging by induction is going to give us those items. Now, what you can do, there's a little device that we keep in the physics lab that's kind of fun. It's a circle device and it kind of looks like an old-timey alarm clock, except on here you've got a piece of metal. And if I bring in an object that's charged, the positive charges, this is going to want to become negative charge because I'm doing this by induction. And these over here become positive charge. And these will actually stand out because they repel and you can actually see that happen. Now, if I actually touch it, I've actually charged my system and my system will actually stay charged and have it look like that. So there's lots of things that you can do from just observations. And so we start electricity and magnetism by observation. And things that we can talk about with those observations are there. But let's make sure we understand that our charge, whether it's an electron or a proton, is going to have a magnitude of 1.60 times 10 to the minus 19. If it's an electron, it's going to be a negative 1.60 times 10 to the minus 19. If it's a proton, it's going to be a positive 1.60 times 10 to the minus 19. The mass of an electron is 0.911 times 10 to the minus 31. The mass of a proton is 1.67 times 10 to the minus 27. So now you're starting to see why I stopped and said, let's talk about our exponents, because as we start to do these calculations, we're going to have things with lots of exponents here. So Coulomb comes out and he's going to make some observations. First observation that he made is that if I have a positive charge and a negative charge, the line that the attraction or the repulsion acts along this line. Because remember, forces are vectors. So they are going to be, they're going to have magnitude and direction. So our first observation that Coulomb had says that. He found, second, that the force is proportional to the charge on the first object times the charge on the second object. And he showed that the force was inversely proportional to 1 over r squared, the distance away from each other. So this 1 over r squared, now you can see why, even though we got with it with sound and intensity of sound, it comes very important when we're dealing with other aspects of physics, because we're going to see this 1 over r squared behavior in a couple of different places. We actually saw it before. Remember that the force due to gravity is Newton's gravitational constant, mass 1, mass 2 over r squared. This is the universal law of gravity. So we get that real important parallel here. So Coulomb said, okay, let's put it all together. The force between two charges is going to be some constant, charge 1, charge 2 over r squared. I'm going to go ahead and write down the other one because I want you to see the parallel. But in our world, the interesting thing is here, mass is only positive. For charges, my charges can be positive or negative. I can have an attraction or a repulsion. So let's look at this. So let's take a charge. We're going to have a positive charge. We're going to separate it from a negative charge. And we're going to have it at 0.25 meters apart. This is going to be a 1 nanocoulomb, and you're going to see these all the time. And this is going to be a 2 nanocoulomb. And we want to calculate the force between these two particles. Well, my force is going to be K, Q1, Q2. This is going to be the magnitude over R squared. So if I do that calculation, K, by the way, K is going to equal 8.9876 times 10 to the 9th Newton meters squared, coulombs squared, or we're going to make it easy on ourselves and we're going to do 9 times 10 to the 9th. So we're going to calculate the magnitude of the force between these two particles. So I'm going to put my 9 times 10 to the 9th. I'm going to have my nanocoulomb here. That's 1 times 10 to the minus 9. This is 2 times 10 to the minus 9. Now you'll notice I haven't put a negative because I'm just doing the magnitude. And then this is going to be my 0.25 squared. Let's look at our units. I have Newton meters squared, coulombs squared. Coulomb times coulomb divided by meters squared. These cancel, that cancels, and I'm left with newtons. So this is all good. And now I'm going to be able to do that calculation. So how I'm going to enter it into my calculator is as follows. I'm going to do 9, and I'm going to use my exponent to the 9th. I'm going to hit enter. I'm going to do 1, my exponent to the minus 9, enter, times 2, my exponent to the minus 9, enter, divided by 0.25 squared. And then I have it out here, but I can change that into my scientific notation. And this gives me 2.88 times 10 to the minus 7 newtons. Now, we know that forces have magnitude or direction. So if I were looking at the force on this charge, the direction is going to go this way. If I'm looking at the force on this charge, the force is going to go that way. So we're going to have to account for the directions of our forces. So we're going to do 1 and 2 dimensions. So we're going to take, this is going to be our charge, and it's going to be a 1 nanocoulomb charge. This is going to be a 1 nanocoulomb charge.
Move it down a little bit.
This is going to be a 2 nanocoulomb charge, and it's a negative. This direction, we're going to say that this is 0.25 meters. That's for simplicity because we've already done a calculation. This is good. This one is going to be 0.1 meters. We are going to also need to know this distance. So we can calculate that distance. R is going to be the square root of our 0.25 squared plus our 0.1 squared. And I get that this is point. Doesn't look right. Hang on. Yep, I guess it is. This is going to be 0.27 meters is our R. Now we're going to find the force on this charge. That's what we're looking for, is the force on this charge. Now we already found, because we found that. So the force between the 1 and the -2 nanocoulomb charge. And this was our K, Q1, Q2, and this is the magnitude, 0.25 squared. That equaled 2.88 times 10 to the -7. Now this one is going to be the force of our 1 times our -2. And it's going to be KQ1, Q2 over our 0.27 squared, because that's the distance between this. So now I'm going to go ahead and plug that in and do that calculation. The answer I got was 2.47 times 10 to the -7 newtons. Now this one can be represented by this blue item. This one is represented by our red. I've got to take into account the fact that I'm in 2 dimensions, and I'm going to have to figure out that one in its vector form. So let's go ahead and put this in its vector form. So F1 minus 2 in its vector form. Now I can figure out this angle. Okay, that angle is going to equal the arc tangent of 0.1 divided by 0.25. Looks like it's 21.8 degrees. So this is going to be 247 times 10 to the -7 cosine of 21.8 degrees, but I'm going to put a negative because this direction's negative. And that's going to be in the I direction. But my y is positive, so it's 2.47 times 10 to the -7 sine of my 21.8 degrees in the j direction. My blue vector, when I put it in, is going to be a minus 2.88 times 10 to the -7 in the I direction. There is no y direction there. So now I can just add my vectors. So this is going to be a negative 5.35 times 10 to the minus 7. Oops. I forgot to take care of something. 2.47 cosine of 21.8. This gives me 2.9 or 2.29 times 10 to the minus 7. This gives me 9.17 times 10 to the minus 8. So now I can add them together. 2.29 This gives me a negative 5.17 times 10 to the minus 7 in the I direction, plus 9.17 times 10 to the minus 8 in the J direction. And that's going to be my resultant force in its vector notation. Now, if I want to find the angle, that's the arc tangent of my 9.17 times 10 to the minus 8. And my 5.17 times 10 to the minus 7. Now I've left out the negative because we know it's going to be in this direction. And I've got an angle of 10 degrees. So the resultant vector is going to be in this direction, where that's the 10 degrees. So as part of your homework, you have several Coulomb's law items that are in there. We will jump into our, you do have in the videos comparing the gravitational force and the electrostatic force. I encourage you to look at that one. These, you do have to do your vector additions in order to get these correct. So you want to look at that. And you do have several of those examples in Blackboard. So questions?
I have a